every triangle has a ink circle that's tangent to all three sides, right? This red circle, center at I, the ink center, it's tangent to AB, tangent to BC, tangent to AC. And then we said there's also some much bigger circles that's also tangent to all three sides, but this time it's tangent to AB and AC on the extensions on the outside, tangent to BC in the middle, but tangent to AB on the extension, tangent to AC on the extension. And the center of that circle is called a X center, facing vertex A. All right, so right now I claim, for example, I said AD must equal to AF. Well, that's because these two segments, they're both tangent to the big X circle, right? Coming out of A, so they must be the same, all right? And then I say, okay, not only they are the same, but AD plus AF is the parameter of triangle ABC. It should equal to A plus B plus C. Why is that? Think about it. This segment, BD, equals BE. Why? Because coming out of B, it has two tangents that's tangent to this X circle, right? BD and BE, so they must be the same. All right? And then coming out of point C, we have this CE, and then this one, CF, they're both tangents, right? So they must be the same. Right? So now you have AD plus AF is literally AB plus BE plus EC, and then plus AC. That is A plus B plus C, no? The parameter of ABC. Right, so this means AD equal AF equal S. S is the notation that we use as a half parameter. So S equal A plus B plus C divided by 2, right? Something that you would use in Heron's formula, for example. All right, very nice, no? Now, if you notice, then I also have something interesting such as BH equals CE. BH equals CE. Why is that? BH is S minus B. That's well known because this is H is the cutting point, the contact point from the ink circle. This is B, so this is S minus B. CE, how do we get the value of CE? So this is AF. It's literally AF minus this B, no? AC, no? So that is, AF is S, no? Minus this AC, which is B. All right, so they are equal. No, they are both S minus B. All right, so the X circle contact point on BC, it's not just some random point, it's the kind of the mirror image of point H over the midpoint of BC, right? If the ink circle contact point is here, then on the right-hand side, the mirror image is the X circle's contact point. And there's something else we can say. How big is this circle? What's the radius of this circle? What is RA? And to get that, let's think about this triangle being similar to this one. Right, they are similar, right? They're both right triangles. They have the same top angle right there, half A. So R divides RA should equal to, for example, AG divides AD. AG equals S minus A. This is S minus A because this is the contact point from the ink circle. AD is S. All right, so RA equal S divides S minus A times R. There is another way to read this expression because S times R is not just something random. S times R is the area of triangle ABC. That's something, that's some significant value there, right? S times R means something, right? It's the area of the triangle divides S minus R, divides S minus A. All right, now if you're curious, because this means that S minus A is this one, no? This times this equals the area of triangle ABC. Like something is happening here, no? Like is there something going on here? And the answer is probably yes. And we should look into next time, but that's you can think about it, and we will look into the area properties next time. But this is an interesting formula and very, very important. All right. Now there's another fun fact. The fun fact is, well, how many? I just draw a X circle facing with the X center facing vertex A. No. So well, then you start to think maybe. What about B then? Do I have a IB? And would I have a X circle that has a radius RB or something? There's nothing special about A. If A has it, then B has it, and then C should also have it, no? And the answer is yes, we should have them. So a triangle supposedly have 3 X circles. Think about this triangle XYZ. The vertex Z is facing, right? This one I would have called this IZ, and then this is RZ, for example, right? Using our previous notation. All right, if you see the bigger picture, it really, for any triangle, it really has 3 X circles. Now it's getting a little bit overwhelming, right? But there's one little property we could prove for now, which is this. The reciprocal of ink circle equals the sum of the reciprocals of the 3 X circles. It's quite straightforward, but if you think about it, well, we figured out what's RA, right? RA is S divides S minus A times R. And if you use the same proof, same method, then you should be able to prove that RB equal S divides S minus B times R, because it's symmetric. There's nothing special for A. Whatever you did for A, it works for B. And it should also work for C. All right? These formulas are symmetric. And if you just use that, right, literally we have figured out, yeah, there are 3 X circles, and we could quickly, identify the size of these 3 circles. We know the radius. Now we just, If you just put in there, you can verify that this is true, right? Quickly, you can see that. Another way to write this is that R divides RA plus R divides RB plus R divides RC equal 1. It's a somewhat important identity for a triangle. All right, next time we should look into something about the area, just in case it's something about the fact that the X circle radius has some area going on here. We should look into this back next time. All right, hope you have fun, and I will see you next time.